Metaverse and chemistry, exploring new frontiers. The metaverse in the context of chemistry. The metaverse, an interconnected network of virtual, augmented, and mixed reality spaces, is not just a digital playground but a transformative ecosystem with significant implications across industries, including chemistry. In a metaverse where science and technology intersect, chemists can leverage immersive environments to visualize, simulate, and manipulate molecular and atomic structures in unprecedented ways. These digital spaces allow chemists, educators, and researchers to step inside molecular frameworks, interact with them, and even manipulate them with real-time feedback. Chemistry, often perceived as a science of the invisible, due to the minuscule scale of molecules and atoms, benefits uniquely from the visual and interactive affordances of the metaverse. By visualizing complex chemical reactions, simulating laboratory experiments, and enabling collaborative research across geographic distances, the metaverse could revolutionize how chemists work, learn, and innovate. The benefits of the metaverse for chemists. The integration of chemistry into the metaverse opens doors to a range of applications and benefits, spanning from research and development to education. Enhanced molecular visualization. Traditional chemical models and software offer static or two-dimensional representations of molecules. In the metaverse, however, chemists can interact with molecular structures in 3 dimensions, providing a clearer understanding of spatial arrangements, bond angles, and functional groups. This is particularly beneficial for studying complex organic compounds, protein folding, and nanostructures, where spatial orientation plays a critical role in behavior and reactivity. Virtual laboratories and simulated experiments. One of the most exciting applications of the metaverse in chemistry is the creation of virtual laboratories. In these digital spaces, researchers and students can conduct experiments that are either too dangerous, costly, or logistically challenging to perform in a physical lab. In a virtual lab, users can work with volatile chemicals without risk, access expensive equipment, and carry out complex reactions with instant feedback. Improved collaboration and remote research. In the metaverse, chemists and researchers from around the world can share a virtual lab space and work together as if they were in the same physical room. This ability to collaborate in real time with realistic visuals and spatial interactions enhances the quality and ease of international research collaborations. Teams can observe, discuss, and alter experiments on the spot, making the metaverse a powerful tool for advancing collaborative chemistry research. Practical applications of the metaverse in chemistry. The metaverse is already influencing various branches of chemistry, including pharmaceutical research, environmental science, and materials science. Here's how. Drug discovery and pharmacology. Drug discovery is a highly complex, resource-intensive process that involves analyzing vast amounts of molecular and pharmacological data. In a metaverse environment, drug researchers can visualize how a molecule interacts with different receptors, predict binding efficiencies, and simulate biochemical reactions with real-time data feedback. This immersive experience can significantly accelerate the discovery of new drugs, particularly for complex diseases like cancer and Alzheimer's, where drug candidates need to target specific pathways and molecules. Green chemistry and environmental modeling. The metaverse offers a platform for chemists focused on green chemistry to model the environmental impact of chemical reactions and pollutants in a virtual ecosystem. By creating simulated natural environments, chemists can predict how certain chemicals will behave in soil, air, or water over time. This insight helps researchers design safer, more eco-friendly compounds and industrial processes, reducing the environmental footprint of chemical manufacturing. Advanced materials design. Materials science often involves creating new compounds or alloys with specific mechanical, electrical, or thermal properties. The metaverse allows materials chemists to visualize molecular arrangements and tweak configurations to optimize these properties. Researchers can collaborate within a shared virtual lab to experiment with atomic arrangements, simulate stress testing, and predict long-term performance, accelerating the design of advanced materials for industries like electronics, aerospace, and automotive engineering. Chemistry education in the metaverse. The metaverse presents unprecedented opportunities for teaching chemistry, making it possible for students to engage with molecules and reactions interactively. Virtual classrooms and interactive lessons. In a metaverse classroom, students can participate in interactive chemistry lessons where they enter molecular structures, observe electron clouds, and see reaction mechanisms in action. By engaging with materials in a tactile, experiential manner, students can grasp abstract chemical principles more intuitively and retain knowledge more effectively. Laboratory safety training. Lab safety training is a critical aspect of chemistry education. In virtual labs, students can practice handling hazardous chemicals, working with lab equipment, and responding to simulated emergencies in a safe and controlled environment. This prepares them for real lab work without the risks associated with handling dangerous materials prematurely. Challenges and limitations. While the potential of the metaverse in chemistry is vast, several challenges need to be addressed. Accessibility and cost. Not all educational institutions or research facilities may have the resources to implement and maintain a metaverse lab. The technology is still evolving, and high-quality virtual reality, VR, hardware, software licenses, and technical support can be expensive, limiting access for some. Technical and computational constraints. Real-time simulations of complex chemical reactions require substantial computational power, and the current technology may not yet meet the demands for highly detailed molecular interactions. Processing delays, resolution limitations, and the need for accurate data input all pose barriers to the metaverse's application in high-level chemical research. Privacy and data security. In a collaborative metaverse environment, data security is critical, especially for proprietary or sensitive research data. Protecting intellectual property and maintaining confidentiality in shared spaces is a pressing concern for researchers and companies working on competitive projects. Future prospects of the metaverse in chemistry. The metaverse holds the potential to evolve from a supplementary tool to an integral part of chemical research, development, and education. Advances in artificial intelligence, AI, VR, and augmented reality, AR, will likely reduce the current technical limitations, creating seamless virtual environments that replicate real-world conditions with high fidelity. As computational chemistry and quantum computing advance, simulations of molecular interactions could reach unprecedented levels of detail and accuracy, allowing for new insights and discoveries. In education, the metaverse could democratize access to high-quality lab experiences, making it easier for students from all backgrounds to engage with chemistry. As technology becomes more affordable and accessible, students from around the globe may have equal opportunities to participate in cutting-edge virtual labs and immersive learning environments. The metaverse offers a promising new paradigm for chemistry, blending digital innovation with scientific inquiry to create immersive, interactive spaces for research, education, and collaboration. While challenges remain, the benefits of virtual labs, enhanced visualization, and real-time collaboration could reshape chemistry's landscape, unlocking discoveries and learning experiences that were once unimaginable. As the metaverse continues to develop, chemistry stands at the frontier of this digital transformation, poised to take advantage of new tools and techniques that will drive the science forward. The metaverse offers chemists a dynamic toolkit for visualizing molecular structures, simulating experiments, enhancing collaboration, and improving education. This chapter outlines just the beginning of what's possible when chemistry enters the digital worlds of the metaverse, a frontier where atoms, molecules, and reactions can be explored as never before.